Good afternoon to all. Welcome to the second session of online FDP on recent trends and innovation in electronics engineering, organized by Department of Electronics and Communication Engineering of IIMT. Dear audience, in morning session, Mr. Damodar Sahu has discussed about artificial intelligence and machine learning. And our next eminent speaker is Dr. Uday P. Singh. Welcome, sir. I would like to give brief introduction about Sir. Dr. Uday P. Singh is Senior Professor and Dean Research at School of Electronics Engineering, Kalinga Institute of Industrial Technology, Bhubaneswar. Professor Singh has obtained his PhD degree in physics from Banaras Hindu University in 1993. He worked with Global Solar Energy for 5 years of thin film photovoltaic. Later, he moved to University of Delaware, USA in year 2000 for postdoc. Dr. Singh joined KIIT University Bhubaneswar in 2002. He has been invited as visiting consultant to Industrial Technology Research Institute, Taiwan in 2008-9. Dr. Singh participated in leadership for academician program of MHRD organized by BHU in collaboration with Nanyang Technical University NTU Singapore in 2019. His research interest involves thin film photovoltaics. Dr. Singh has published nearly 100 papers in peer-reviewed journal. Welcome, sir. Now, I would like to invite our FDP convener, Professor Dr. Seema Nayak, to welcome, sir.
Thank you, sir. Very good afternoon to all, and I hearty welcome our today's speaker of session 2, Dr. Uday Pratap Singh, and also I welcome to all the participants from the different region of the national India and also international. Today's topic is very interesting, that is a VLSI design, and it's a very vast topic. And also in this session, we can clear our queries, that is there are so many challenges to implement the VLSI architecture. Also the design complexity is growing when the technology is scaling. All such type of queries we can clear in this session. And now I welcome Dr. Uday Pratap Singh. Please, sir.
Good afternoon. First, I would like to thank Dr. Seema Nayak for inviting me to this give a talk on FDP. So I will be speaking mostly on our research part, which I am doing. So can I share the screen? Okay. So I will be talking about the thin film solar photovoltaic and what is its future prospects. Like those who are not very well versed with this solar cell area, they must be familiar with only the silicon solar cell, which are more visible at different places, because government of India is also promoting this solar energy a lot. So we work basically on the thin film solar cells. I belong to the School of Electronics Engineering, KDM University, which is also Institute of Eminence. This is just an overview of our university. It's founded by Dr. Achyut Samant, who is a noted social education student. Now he is also an MP from the Odisha. This institute is also declared Institute of Eminence by MHRD. So giving an outline of my talk, I will just briefly introduce about the photovoltaic approaches are there, and then a brief on the silicon solar cell, which is very common, and then I will move to the thin film photovoltaic. So I have taken 3 materials: copper, indium, gallium selenide, copper, zinc, tin sulfide or selenide, and then the cadmium telluride. So if time permits, I will try to cover all the 3 in this. So it will be a general view, not very detailed physics or something, because audience is not very focused on the solar. So I will have a brief, a general view on this topic. So if you see the photovoltaic is basically it's a wide variety of renewable energy projects and most promising as a future energy technology due to it's a pollution free. The input energy is abundant, available everywhere as the sun. This also can operate in diffuse light. Only problem with the photovoltaic system was the high price of the solar module, but now the silicon solar cells are also like when this Chinese government have pumped a lot of money into the photovoltaic, so the module cost have reduced drastically. So basically one of the major is the cost reduction of the solar cells so that everybody can use at their home. If you go into a slightly brief history of this, in 1839, the photovoltaic effect was discovered by the Becquerel. And then people don't know, like in 1883, the first solar cell was built, which was basically a selenium layer. On top of that, some gold leaf was plated, and then it gives efficiency of around 1%. But the breakthrough came in 1954, which is the modern age of solar power technology, Bell Lab. So they have shown that the silicon doped with certain impurities were very sensitive to light. From there, the silicon photovoltaic has come into the picture. So if you see the importance, so direct conversion of solar radiation into the electricity, no mechanical part, moving part, no noise, no pollution, and PV modules have a very long lifetime. Generally, the manufacturer gives around 25 years to 30 years of lifetime for these modules. With a certain reduction in the efficiency. The energy source, the sun, is free and inexhaustible. It's very flexible energy source. You know, like you can use into your microwatt into your calculators, and then megawatt plants are also installed. So what is the, like, if somebody wants to do like solar cells, so what are the requirements? What you look for the materials? So the materials, like semiconductor materials, which has generally the band gap between 1.1 electron to 1.7, because it take care of the solar spectrum what is available. One needs a direct band gap structure for higher energy conversion, but you know silicon is an indirect band gap, but still it is used as a dominant into this. Okay, easy reproducible deposition technique suitable for large area production. If you are trying to go for this, so it should be easy and reproducible deposition technique. How you can make, how you are going to make this, and then good photovoltaic conversion efficiency. And one also look for the long-term stability. Otherwise, if its stability is not there, then it's very difficult. People will try to go and buy it. Just to a brief on the how it operates. Basically, when the sunlight falls on the PN junction, or because your solar cell is a PN junction, it generates electron hole pair. So electrons are being collected at the N side and the hole on the electron on the N side and the hole on the P side. So that is the collection of light generated charge carriers. Then generation of voltage across the solar cell, and then this dissipation of the power into the loads. So basically it consists of three processes: light generated charge carriers, collection of the charge carriers to generate current, and the generation of voltage across the solar cells. So I'll skip this. So now major concern is the efficiency of these solar cells. So what is the efficiency? Is basically fraction of incident light energy converted to electrical energy. So what light is falling on your device, how much it is being converted to the electrical energy. So efficiency is the most important parameter because it allows the device to be accessed economically in comparison to other energy devices. Because if it is not economic feasible, nobody is going to buy that. And for a given solar spectrum, like if you have a sun, it has certain spectrum. The efficiency depends on your semiconductor material. That is basically the band gap of that material. It's a direct band gap material or indirect band gap material. Then the device structure, how the device is formed. Then the ambient condition, at what condition you are working on this. Then the high radiation damage, like if you are using the solar cell at the space application. So radiation damage is also a concern. And then the sun spectrum, what sun spectrum you are getting. Like in European countries, you know, like you don't get the sunlight throughout the year. So efficiency alone is not enough. The cost of the cells is also important for, and the lifetime. So 3 parameters: efficiency, cost of the cell, and the lifetime, that is the stability. So if you're looking for the different approaches, okay, so there are many approaches to make PV cells, and if experts do not agree on which one is the best, because if I work in silicon, I will say silicon is best. If somebody works on thin film, they say like thin film is best, and it's coming. And then the concentrated power for concentrated photovoltaic. Okay, so I will not be discussing about this. Our focus will be on mostly on the thin film, which is comprises of amorphous silicon. Then you have the polycrystalline materials, and then there are a lot of work going on the organic, and now recently a lot of work has been on the perovskites. So if you see the overview, so first generation was a silicon single crystal silicon wafers, and still the silicon is dominant. More than 90% still you are getting from the silicon. Second generation come amorphous silicon, and then you have some polycrystalline silicon, and then the cadmium fluoride solar cells, and then the copper, indium, gallium diselenide solar. In third generation, one get the nano crystal solar cell, then grid gel cells, and then the polymer solar cells, dye-sensitized solar cells, and the perovskites. They belong to third generation. And now the fourth generation is the hybrid inorganic crystal with the polymer matrix, and also the tandem. People are going for the tandem solar cell so that can capture the maximum solar spectrum. Because if you have a fixed band gap, you will get the that range of solar spectrum. If you have a variable band gap, you can capture most of the solar spectrum in your device. So I will just, as I told, like I will just going through the briefly about the silicon solar cells. So cells are typically made with the crystalline silicon wafer, and these wafers obtained from a large cylindrical monocrystalline ingots. Like this type of ingots are grown by the Krolowski growth process, and then directional solidification or casting produce large grained polycrystalline single ingots. So it is, if you go for polycrystalline, it reduces cost by around 40%, but the efficiency become less. So ingots can be either single crystal or monocrystalline or the multicrystalline. So most common approach to process discrete cells on wafer short from the same. So if you try to cut into the, you saw it into different thickness. So if you see in the brief, you start from the silicon feedstock, then you melt it in a certain, that is a Krolowski crystal pulling process. Then you get ingot, big ingot, more than this 6 feet, 7 feet. And then from there, you cut a slice of wafers, you process it, and then you get a solar cell, solar module, basically. In this case, what is happened, like if you have a, in silicon, you have a different silicon cell, and then you integrate it. Okay. Similarly, you have a polycrystalline, you have grow, the material will look differently like this. It's not a single crystal. Again, then you can have a polycrystalline module. This process is slightly cheaper, but efficiency is slightly reduced. So this is basically a brief about the how the silicon solar cells are processed. What you always see on certain rooftop, even the government building now, people are putting the solar cells. So how this crystalline silicon solar has developed, if you see, there are two things. One is the wafer thickness, another the silicon usage. So wafer thickness is, this is the wafer thickness, which has earlier it was around, in 2004, people are using 400 micron. Now it has reduced to around, let's say, less than 100 micron. So people are using less than now 100 micron of silicon wafer. And then if you see the usage, gram per watt, like you want to develop 1 watt, so how many grams are required of silicon? So it is now almost constant, not much reduction after, let's say, 2008. It's nearly the same. So why crystalline silicon is so successful? Because it's a high module efficiency. It gives around 20%. It has high stability and reliability. Mature and modular technology. It has been researched a lot. So if you want to set up a plant, next day you can buy a certain ready-made plant and you can start production within 6 months. No environmental concern. and white material available. It's from this silicon you get from the sand. So when you are trying to look for some other material, so you have to look for the similar advantages. Otherwise, not going to be as successful. So only weak point for silicon was that it is indirect band gap. So the low light absorption coefficient is slightly low, and the cost. But now, like for last 1 or 2 years, the cost has come down drastically. So as I told, like I will be discussing about thin film. So what are the advantages of thin film? So I am going for thin film, so it has to compete with the established crystalline silicon technology. And one has to achieve comparable performance with the promise of substantially lower cost. Then only can compete with the silicon. High production capacity with the reduced material consumption. So material consumption should be reduced, and energy input the fabrication process. Lower module cost for large area terrestrial application. So module cost should be, for large area terrestrial, you should have a lower module cost. Some of the advantage, what has like thin layers in silicon, you have seen like less than 100 micron are still needed. But for the thin film, you need 1 micron to 5 micron thickness only. So material cost, low material cost is there. What happens here, the continuous large area manufacturing is also possible. In like silicon, you have different wafers and then you try to integrate the wafers in a module. But here you can have a continuous large area deposition. And cell interconnects, you can produce monolithically within the module. Flexible and lightweight modules can also be made. And these thin films module are aesthetically superior, which gives the advantage for BD integrated applications. You can get it coated on the window panel also. Applicability in roll-to-roll production is also possible. And then it has a potential in the tandem applications. This gives the, from the NREL, National Renewable Energy Lab of USA, they try to update the efficiency of highest efficiency of different solar cells. So these are the different solar cells. So we are concentrating on the thin film photovoltaics. So if you see this CIGS or the copper indium gallium selenide and the lab scale, the maximum efficiency achieved is around 23.4. Cadmium telluride is around 22.1% is achieved. Copper zinc tin selenide, which has been in the process, but the efficiency is around maximum is reached around 12.6. So still people are working on that to get a certain enhanced efficiency. In the meantime, perovskite has come. So perovskite, you can see like 25.2 on a small area. And then if you are using tandem means on silicon, you will grow perovskite. So efficiency increased to 29.1. So perovskite and CGTS people are still working on that. So if you want to compare the efficiency technologies, best lab cells and the best modules. So if you see the single crystal, 79 centimeters square, which is produced in the lab, which gives around 26.7% efficiency. And the this area, 13,177 centimeters square, gives you 24.4. When they go to polycrystalline or multicrystalline, the efficiency is slightly reduced. 4 centimeters square in the lab gives 22.3, but modules 99.9. When they come to CIGS, 1 centimeter square is around 23.4, which is the highest achieved, and the module is around 19.2. Cadmium telluride 1 centimeter square gives 21, but the module can give you 19. So difference is not too much. Whereas perovskite, you see, the highest achieved is 21.6. This is the 1 centimeter. What you have seen earlier, it may be less than this area. So here what you are comparing the 1 centimeter square or more. And the perovskite module give you 16.1. So this is the lab scale and how we are going to convert into a module. What is the difference coming? As shown earlier, like crystalline silicon, you need around more than 100 micron, whereas thin film, you need a very 1 to 5 micron only. So the main thin film technologies were amorphous silicon, which is now it's almost dead now. No company is working on this now. Cadmium telluride, only First Solar company is working on that. and then the CIGS. So I will show you like what are the different companies working on the copper indium gallium selenide. So these are the 16, like what is the share? Crystalline silicon you can see 91. So not much has changed. Amorphous silicon may have reduced from 2% to less than 1%. So maybe it has gained around more than slightly between 5 to 6%, and CIG is still 2%. So there's not much change in the market share of this solar cells. If you see the production, that is this, you can see like this. This is your CIGS, which is around less than 2%, and then this is your basically small is your amorphous, going to dead. Maybe 1 or 2 years there will be no amorphous silicon module. If you see the annual global PV production, so cadmium telluride is rising. Okay. CIG is slow moving, but this amorphous silicon is now going down. So maybe by 21, 22, nobody is going to make amorphous silicon. So cadmium telluride and the copper indium gallium selenide photovoltaic modules have the potential to reach cost-effective PV generated electricity, and they have transitioned from laboratory to the marketplace. And the transition from the lab to manufacturing has been much more difficult than what is anticipated. So I will now be going to the CIG solar cells, and we'll discuss in detail about this copper indium gallium diselenide solar cells. So these are the some of the highest efficiency achieved, because you see the mini module is you get 19.2, which is the highest efficiency. Copper indium gallium selenide, there are different ways. Now there are different ways to manufacture this copper indium gallium diselenide. If you do by sputtering, the highest achieved is 16.7. If you go by the co-evaporation method, so recently it has been updated to 23.4, which is the highest. And there are certain, like here what happens, like copper indium gallium selenide is a p-type material. So you have to make a PN junction. So N is mostly cadmium sulfide is used for making a PN junction. So in this case, like Japanese don't, because cadmium is slightly carcinogenic and toxic. So Japanese people, they don't use cadmium. So it is a cadmium free. Here also one has achieved the 22%. And also you can grow this on the polyamide substrate, polymer. So the lab scale, the highest efficiency achieved is 20.4. This was the module 19.2, the solar frontier, which has achieved this module. So if you are looking for this crystalline silicon, and then we try to compare with crystalline silicon, 75 onward is around more than 20%. Okay, small area. But like CIGS, it has started in 76 or 77, and then now it has gone more than 23%. So there are different process steps. Like in this, within this region, 95 to 2012-13, people are using the 3-stage process. I will discuss that. And after that, people are trying to use alkali metal and then post-deposition treatment. So now this is the standard process, which are giving more than 22% of efficiency lab scale. So if you see this material, what are the material? Which is basically copper indium diselenide. Now if you replace some of the indium by the gallium, it becomes copper indium gallium selenide. So you can vary the band gap of the material. It's a compound semiconductor of 1/3 and 6th group. It's basically heterojunction. Silicon is a homojunction, because you take a silicon wafer of p-type and then you diffuse n-type. So it's a homojunction because silicon, but it is a heterojunction. You have the copper indium gallium selenide is a p-type material, then you have a different n-type material. So when you are making a p-n junction, it's a heterojunction. High efficiency, more than 22% small area and 60% large area module. Very good stability in outdoor tests. If you see the application, you can use in solar power plants, power supply in aerospace, decentralized power supply. So these are different applications one can use. You see the crystals, that is the structure is basically the copper-based chalcopyrite material. Okay, so copper, indium, and selenide. Now, if you try to replace some of the indium by the gallium, you get the copper, indium, gallium selenide. So you can, this is the 1 electron volt, but you can go more than 1 electron volt. You can also replace selenium by the sulfur, so you can increase the band gap. But other problem comes into there. So best efficiency one achieved for the around 1.2 electron volt. You see the material, as I said, crystal structure is hexagonal chalcopyrite structure, which is derived from the cubic zinc banded structure, which is tetrahedrally coordinated. It's a direct band gap semiconductor. Band gap you can vary from 1.04 to 1.6 electron volt by replacing indium by gallium. If you have copper gallium selenide, it will be around 1.68. If you have copper indium selenide, it's 1.04. Exceedingly high absorption coefficient is very high for this material. Absorption length, so you can absorb most of the spectrum within the 1 micron thickness. So minority carrier lifetime, which is several nanoseconds, because important, as soon as you generate a charge carrier, it has to be collected. So it depends on the carrier lifetime and the diffusion length of the charge carriers. So only problem, or what you can say, to have a pure phase. If you see the phase diagram, if you want to have a pure phase alpha, which is the alpha copper indium selenide. If you go beyond this, copper is more than 25%. You have this copper indium selenide phase plus this copper selenide, which is very highly conducting. So you will get a shorter device. You will not get any solar cell. If you go below this, less than 22%, you are going to generate certain defect states. So range is between, best range is around 24 to 24.5 atomic percent of copper. So for optimal range efficiency, you can get between 22 to 24. So while growing this material, one has to be very cautious. Like you have to be, copper should be between this. And possible at temperature growth, 500 to 550. Otherwise, you get the beta phase, certain vacancies, copper vacancies, indium replacing the copper, which is antisides. You get the delta phase also built by disordering copper indium. So these will create all the defect states into this. Now, if you are more than 25, you get the copper selenide phase, which is basically highly conducting material. So problem is that alpha phase is highly narrowed at room temperature. So people have tried to see like how we can increase this range. So partial replacement of indium by gallium, it has increased that range. So in this case also, you can only replace 20-30% of indium. If you replace more of the indium by gallium, you are going to increase the band gap, but there are certain defects again introduced. And people have also shown that sodium, which is around 0.1 atomic percent, if you put into this, it will also try to slightly increase this range. It will give a better morphology, passivation of grain boundaries. It will have a higher p-type conductivity and reduce defect concentration. So I'm not going into detail how this works. So this shows the how the band gap can vary from 1.4 to 1.68 if you are replacing indium by gallium. Okay. And this is just the quantum efficiency showing the different band gap. Because it has a high optical absorption coefficient. If you see the silicon, if you want to absorb 100% light, you need more than 100 micron of the material. But in case of cadmium telluride or CIGS, you can see if you have around 1 micron, you are able to absorb most of the solar spectrum. So it is very high absorption coefficient material because they are direct band gaps. Silicon is indirect band gaps. That is one of the difference. Is optical absorption coefficient slightly less. So if you are going to make a typical device, so you have a substrate. To take a substrate, which can be a soda lime glass or a polyimide. On that, you have to coat a back contact because the PN junction, then you have to take a contact on both the sides. One is referred as the back contact, other is the front contact. So molybdenum is used if one can deposit by the sputtering. Then you have a p-type copper indium gallium selenide, which is also referred to the absorber layer because they absorb most of the light. Then you have a n-type material, which is commonly used as cadmium sulfide. It's a thin layer. Then you have a transparent conducting oxide, because light has to pass. It should be conducting also, and light has to be passed, because you know there is a trade-off between this when you are trying to make a transparent conducting oxide, which are also used in your mobile smartphones, because you tap, you can see the numbers, all this. So it should be transparent also, and should be conducting also. So there is a certain trade-off, so that because if you use a direct metal, no light will be absorbed, all will be reflected back. So a transparent conducting oxide is used, and if it is a slightly large area, you try to put certain grid so that you can collect the current from all over the area. So light is solar spectrum is coming this way. It is a higher band gap. Maybe a TCO is around 3.6. So most of the light will pass. Cadmium sulfide is around 2.4. Still some light will be absorbed, but most of them will pass, and most of them will go into the absorber layer. I just shows the band gap, like 1.2 electron volt, 3.3, 2.4, 1.2. So I'll not be focusing more on this. Skip this. So if you see the processing step for this, like when you're trying to make, so back contact, mostly is done by the sputtering technique. Then you have the absorber deposition, like copper, indium, gallium, selenide. So you can do by co-evaporation. Co-evaporation means you are trying to evaporate all the four materials simultaneously. Other method is sputtering plus selenization. So you try to sputter this copper, indium, gallium, and then in the selenium you try to selenize it. There are processes also like non-vacuum process, where you can use the nanoparticling and then print it, or electrode deposition, and then you can again selenize it. So there are different processes used, but like if you go for those who are going in the industry, is mostly the co-evaporation, the sputtering and selenization. Then you go for the N-type material, which is generally referred as the buffer layer also. So cadmium sulfide is mostly used, and Japanese use this hydroxide, zinc hydroxide, or the indium hydroxide compounds. They don't want to use cadmium. And on top of this, to try to have this ITO, indium tin oxide, and or the aluminum dope zinc oxide as a transparent conducting oxide, again deposited by the sputtering, and then you can manufacture this. So this is the simple step one can process through this. So in this case, I will try to go through different, like if you are trying to have a moly, why you want to have a moly? So what, and then why you have what are the different processes here, and then cadmium sulfide, how it can be deposited, and this. So back contact. So first one, what we will see, like what is this requirement? So it should be chemical stable in the selenium atmosphere, because you're trying to selenize it. It should have give a good ohmic contact. If it's not a good ohmic contact, we are going, it's high resistive. And then the adhesion and the structure is way. Adhesion should also be very important, because it should not happen like after a few days the film has come off. So adhesion is also a very big parameter. So why moly? Why only the molybdenum are using? So during the different research, people have come to the conclusion that it is stable at a processing temperature, resistance to align with copper and indium. It gives a low contact resistance to the copper indium selenide. Conductivity, and also the conductivity do not degrade during the processing step. So one can deposit generally this bilayer. Typical deposition is a bilayer. Why bilayer is used? Generally they deposit first layer at high argon pressure and second layer at low argon pressure. So to reduce the stress between the film. If you have a large stress in the film, maybe it will peel off after a certain time from the substrate. So deposition generally is done DC magnetic sputtering 2 to 4 passes over target, high power, low argon pressure, low power, high argon pressure. So one will give you the compressive stress, other will give you tensile stress. So you will try to reduce the stress between the film. So your adhesion will be much better. Now, if you are using a co-evaporation, so there are 4 sources for the 4 different material. It's a thermal evaporation. You have a film growth monitor. You can monitor what is the rate at this are going. Substrate you can keep at here, and then on top of that you can also have a substrate heater, which can be working at 400, 500, what is the required. So you have independent control of each element, film composition, gradients, enables possible benefit of copper rich growth. So you can vary this different parameters. This is one of the system which we have in our lab here in KIT Bhubaneswar. So these are basically the 4 sources you can see. You can have one material here, one material here, one material here, one material. So all these are the power supplies for each sources. So you can simultaneously deposit this. So this is funded from the DRDO. So different in the co-operation, basically what happens, different variation one can have. Okay. Initially what is started is you have substrate temperature constant, selenium is still constant, and also you are depositing copper, indium, gallium as a constant. So you get a band gap, so no grading. After that, there was a bilayer or the Boeing process, because Boeing company has given this process. So what happens here? You have the selenium flow constant, but initial what you have substrate temperature is lower, and you have more copper and less indium gallium. After that, you raise the substrate temperature to 550 and reduce the copper at this stage, and you increase the indium gallium, and finally reduce it. So you get a normal grading structure, which was the Boeing process. This has gone. But in 1991, NRA US, they have discovered a 3-stage process. In this, what happens? They have the selenium flow constant. Here, the temperature you can see is lower, and there is no copper. Initially, they don't deposit any copper, only deposit indium gallium. As soon after a certain time, they increase the substrate temperature and they increase the copper, whereas they reduce the indium and gallium. And the 3rd stage, again, they raise the indium gallium, reduce the copper to 0. So that's how they get a double grading structure. So the possibility can control the gallium gradient. So this has given the best structure, best device. Other method is the sputtering and salinization. So it's a sequential process, because you salinize from vapor. So you take the substrate, you deposit copper, indium, gallium by sputtering, and then you try to salinize with the hydrogen selenide or selenium vapor. So large area deposition. Only disadvantage is hydrogen selenide is very toxic gas. So people have tried to replace this selenium. So same process there. What happens, like now they deposit the selenium on top of this. They are not using hydrogen selenide gas to avoid the toxicity. So they deposit selenium layer by evaporation. And then they rapid thermal process they use for annealing. So large area, avoidance of toxic H2SE, and you get a good compound. So this is the second method. So these 2 methods are more familiar. But if you see this non-vacuum process, people have thought like because you can control the composition very well, improved material utilization. In sputtering, like if you are using a sputtering target, only 40% use, 60% is lost. But if you have a manufacturing unit, you can have a contract with the supplier, so where you can give the target again and then you can buy back. But if you are lab scale, it's all the disadvantage, because 40% is only used, 60% is waste. So people have found like if you are using a non-vacuum process, so you have a improved material utilization, improved uniformity, and reduced process cost. So this approach has been used by the 2 US companies, but efficiency wise, like small area, this is okay, but large area production, this was not given. Commercialization wise, it's not good. Now coming to the N-type material, which is the cadmium sulfide, is generally deposited by the chemical bath deposition. Okay, so simple setup where you have like a water bath in which you keep a beaker. There is a coated magnet which is rotating, and you try to dip your substrate. So solution, you use the one is the cadmium source, so cadmium sulfate. On other cadmium source, you can use the ammonia and the sulfur source. After that, before the transparent conducting oxide, people have tried to use one layer of highly resistive intrinsic layer. What happens here if you don't use this intrinsic layer, highly resistive intrinsic layer? What happens, like, because when you're depositing, there may be chances you have some pinholes, some defects. So when you deposit the contact, so there may be some shunting path. Okay, It may not be visible. It may not be like when you are measuring this now. Maybe after 1 week when you measure, it may have shorted. So people will try to, what they have tried to do is that they have tried to coat this with a highly resistive N-type zinc oxide. So it will avoid the shunting path. So you can see, like if your intrinsic zinc thickness is 70 nanometer, you get this good factor. But if you increase this thickness, your fill factor will reduce. And then transparent conducting on site is mostly zinc oxide, aluminum dope zinc oxide. The second layer is aluminum or boron dope, use 350 to 500 nanometer. Thickness and material property of these are determined the trade-off between transparency and conductivity, as I told you earlier. Because if you want to have more conductivity, your transparency will reduce. So there is certain trade-off. So you have to optimize between 80 to 90% transparency and the conductivity of certain range. And finally, if you have trying to have a large area, so you have try to put certain metal contacts so that you can collect the current from all over area. Okay, so if you lab scale, if you are making, we try to make certain here, then we try to have a small cells for the measurement. And if you are having a module, so you can integrate that module by the laser scribing. You start with the glass substrate, then you scribe it, you isolate the moly, then you try to deposit the copper, indium, gallium selenide, and high resistive zinc oxide. And after that, again, you have the second scribing isolation, and then finally you coat this tissue, then you have the different cells. So here you have an interconnect are possible only on the large area, but in the silicon, you have to have different solar cells, and then you have to integrate. This is one of the device we have developed under the DRDO project is around 11.1%. So if you see this, as I told you, that there are different methods: co-evaporation, sputtering, electrodeposition, printing, and substrate wise also you can deposit on glass, you can deposit on the different other material like molybdenum sheet or stainless steel sheet or the polyamide sheet. So these are the different companies which have started depositing making this EIS solar cell. By co-evaporation, these companies are there. But now most of them have closed, very few are surviving. Now this gives you the substrate wise. Glass, so this many companies are working on the glass. Most of the companies have merged or they have stopped. Then one can have stainless steel substrate, Neosole, Global Solar or this, and copper or the aluminum sheet or the plastic. So these are the different companies which are working on different materials of the solar cells. But recently what you see, this is the 29 November updated. So you can see the Solar Frontiers on copper, indium, gallium selenides are making something, and then Neosole, this, and the cadmium, and then Solibro. 3 companies are in the manufacturing. Most of them have merged or they have sold out. And cadmium telluride, you have the first solar. Most of these companies are on the silicon solar cells. Different types are the different type of method they've used for the crystalline silicon. So I will skip this sodium, which was not necessary. So what you have seen, like this is the basically processing step for the polyamide. In the polyamide, you coat the moly, then the CIGS, because the polyamide material cannot go higher temperature more than 400 degrees. So you have to have low substrate temperature. Then they deposit the potassium fluoride or the sodium fluoride, which is, and then they do the post-deposition treatment. So they have got around 20.4 in 23. Now they are also in the module production. So this is now the standard after the 2016. You have a glass or metal plastic file, somebody wants to start, then you have a molybdenum as a back contact. Then moly selenide generally is formed between this copper gallium selenide and the moly during the process. So you have a copper indium gallium selenide, which is around 2 micron. Then you deposit some alkali metals. Then you have the cadmium sulfide, and then you have a zinc oxide intrinsic, and then the top transparent content. So this is the standard what is now being used. But still people are trying to play with certain other, try to do with certain other material to enhance the efficiency, but there has not been much success on that. But lastly, 2016, they have the success of depositing the alkali metal and then trying to annihilate. So advantage of these flexibles are low weight, adaptation to non-planar surfaces, new application, roll-to-roll processing is also possible. Because if you use the glass substrate, roll-to-roll processing is not possible. Potential for reduced energy payback time. Energy payback time is that like how much energy you have used to create the solar cell and within how many year or time or months you can recover that much energy. Okay, so silicon has a energy payback time more than this copper indium gallium disarmides. There are certain challenges also. Limited source temperature because plastic substrates don't go around above 400. Diffusion of impurities, metallic substrates, improvement of open circuit voltage and short circuit current, then the encapsulation. So these are certain challenges still exist in this material. So if you see now these many companies are still left with this, those who are working. So challenges I have already discussed, so I will skip this. Now people are thinking like if you want to go for terawatt or gigawatt, so the problem may come with the indium. Indium ability will be gigawatt level is not a problem, but when you go terawatt, it may be a limitation. So people try to see like what can be other alternative. So they try to replace indium by the zinc selenide. So you get the copper zinc tin selenide. What is the CZTS? Okay. And people have also tried to have a ultra thin CIGs, but manufacturing is difficult. Lab scale you can get, but manufacturing is still a big problem. These are some of the application of the CIGS solar cells around the globe. Now this CZTS, casterite, like if you are trying to replace indium, so again it's a direct band gap material, copper zinc tin selenide or copper zinc tin sulfide. So you can vary the band gap from 1 to 1.4 electron. This also has a high absorption coefficient. It's again a p-type semiconductor. Zinc is abundant. Tin is also abundant in earth. So they are earth abundant material. So limitation, what are the limitation for this? So one has to have a deep knowledge because a lot of research has to be done. Process better suited for casterites, better contact materials. And then there are only problem with the different secondary phases are formed in this material. So structure wise, again, it's same. You deposit the glass, then you have the back contact, then the absorber layer, and on top of this, you again have the cadmium sulfide on this. If you see the efficiency wise, only 12.6 at the lab scale, that has also been achieved in 2014. Now 14 to 20, 6 years have passed. Nobody has crossed this limit. A lot of work is being going on, but this efficiency has not been improved. So there are three variants. One is the copper zinc tin sulfide. So people are using different methods, sputtering, electrode deposition, solution-based co-evaporation. So using this method, the highest efficiency achieved is around 9.24, which is again way back in 15. If you have this variant, copper zinc tin selenide, here again the different method when we use, the higher efficiency achieved is only 11.6. This 11.6 has been improved to 11.7, not much. And now if you have this copper zinc tin sulfur selenium, so higher efficiency is 12.6. This is the highest achieved in 2014 only on a small area. And this last 6 years, this has not been improved. People are struggling. They're trying to get around 9 to 10% only on the small area. So there is no possibility of any module manufacturing also. Even the Indian government has found a lot of money onto this. A lot of project has been sanctioned on this copper zinc tin selenide from the Ministry of New and Renewable Energy, even from the DST. We have also run one project on this. So still a lot of problem is there with this material. So it's a p-type semiconductor, same structure like what we have seen in the CIGS. Only thing indium and gallium are replaced by the tin and zinc. Structure wise also same. You have the soda lime glass or the polyimide substrate, then you do molybdenum deposit as a back contact, then you have the absorber layer of copper zinc tin sulfide or selenide, then cadmium sulfide to make a PN junction, then you have intrinsic zinc oxide and the aluminum doped zinc oxide. So structure wise again same, but only problem is that they have large number of secondary phases of the defect state, which kills the efficiency. So I will just skip this. That people have tried to replace some germanium. Okay. So CZTS is basically new emerging technology, but still a long way to go into this. Now coming to the third material, which is the cadmium telluride. So I will briefly go on to this cadmium telluride. I think I still have 8 to 10 minutes. So I will try to finish within time. So this is the most successful thin film solar technology in production. Okay. So First Solar is the company, because still they have the bumpy rides, like earlier it was MTech, then goes to Golden Photon, then the British Petroleum, then the General Electric, and finally to Solar Cell, which is now referred as the First Solar. So these many companies have started on the cadmium telluride. They all have closed. Only the First Solar is surviving, and they are having manufacturing. They have manufacturing plant in US. They have manufacturing plant in Malaysia also. One of the advantage here, like people have find, like if they treat the cadmium telluride with the cadmium chloride, that improves the efficiency, because it gives it's a flux agent basically. Have a grain growth. So that is a breakthrough into this technology. Now you know, like 22.1 around 0.48 centimeter square is highest efficiency achieved. So module wise, they are around 17 to 18%, but in regular production, they may be around 14 to 15%. Again, we know that ideal band gap is 1.4 electron. Cadmium telluride is having a 1.44, nearly 1.5. So again, a direct band gap semiconductor. Requires only 2 micron thickness, and you know only 2 materials are used: cadmium and telluride. In CIGS or copper indium gallium selenide or copper zinc tin selenide, they are having 4 materials. So control the composition is difficult task in that materials. Composition control is one of the major challenge there. But here only 2 materials, you can have control is quite good. Cheap to produce, less energy needed to produce, and easy fabrication. Only problem with this cadmium telluride is the ohmic quantity. So work function is very high, 5.8. So generally you don't find any suitable metal for forming ohmic contact. So that is the biggest problem. But still, people try to have certain other methods and then try to coat the metal on this. So need to form intermediate layer to get tunneling contact. Okay, so you don't directly deposit metal on the cadmium telluride. You try to have some interlayer between that. So this requires use of inverted structure, where CDT contact formation is the last step. So cell formation, again you start with the substrate. Common soda lime glass is used. What is used in the window? Contact. Then on the soda lime glass, you have a transparent conducting oxide, which is fluorine doped tin oxide. Can be deposited by different methods. On top of that, you deposit the window layer, which is cadmium sulfide. Again, it can be deposited by different methods: sprayed, sputtering, chemical bar deposition, electro deposition. CSS is the closed space sublimation. First Solar is using closed space sublimation. Then you have the absorber layer. You can also be sprayed. People are not using sputtered or the CSS. The First Solar now is using the closed space sublimation process, because that's the only company which is surviving. So production technology, you glass, then you have the TCO, then you bus bar, then patterning. So this is the step you get the final module. Structure wise, if you see, if you have a glass, you have a transparent conducting outside, you have a buffer layer, and then this cadmium telluride. It says only this cadmium sulfide and cadmium telluride interface, because due to intermixing, some interface is formed, and then back contact. Slightly people have tried to do copper loop. So light goes this way. So one of the advantage here was that earlier when you deposit the cadmium telluride, you have this structure. But when people have found, like when you treat with the cadmium chloride, you get a very large grain. So that was the achievement achieved in the 80s. Now this is the common process used. Okay, now we can have a substrate structure also. So further improvement is still needed. Like cadmium chloride has not reached to that maximum efficiency. So performance so far has resulted to the increase in the short circuit current. So still there are certain room to improve the open circuit voltage by 15%, because if you see the band gap is around 1.5 electron volts, so you can maximum open circuit voltage one can achieve is around 1 volt, but still 750 or 850 millivolt is used. Okay, so this is the last slide. So as I am working on the thin film, we say like thin film have the greatest potential for low cost production and will dominate the future of the photovoltaics. Thank you. I will try to acknowledge like my PhD students and the funding from the Ministry of New and Renewable Energy and the Science and Engineering Research Board of this. Thanks for your questions. If you have any questions or anything, how I don't know how you are trying to link it.
Thank you, sir, for discussing a very happening topic. There are a few questions, if you permit, I would like to ask.
Yeah, sure.
Sir, first question is related to efficiency. Why efficiency of solar cells are very less, and can be improved by doping by some other processes?
If you, because there are certain limitations, so there are certain theoretical calculation has been done. So theoretical maximum efficiency one can achieve is around 33 to 35%. And then when they are doing this, now I have the slide. So there are certain losses again. There are certain losses into the back contact. There are certain losses into the absorber layer, because you cannot, what charge carriers are generated, you cannot collect all of them. So you have certain losses also there. Then you have certain losses into the cadmium sulfide, because a solar spectrum has different wavelength. Wavelength is absorbed in the different layers. So there are certain losses, but still people are trying to dope with certain material, try to research on that, try to have some theoretical studies so that how they can achieve.
Okay, sir. Next one is, sir, you have discussed about environmental concern. Then question is, what are environmental concerns with solar cell application point of view? Where we can use solar cell?
Application point of view, solar cells are being a terrestrial application. Like people are trying to generate, like if you see the Indian perspective also, like government is focusing on to generate lot of energy through the crystalline silicon. So crystalline silicon also they can be recycled, because if you say like after 25 years, if you are creating 1 megawatt, because last month Modi has inaugurated one solar power plant. So if you have, let's say, 1,000 modules, and after 25 years they are waste. So there are certain studies also going on the recycling.
Okay.
It's not like it's really wasted. You have to recycle. Like if you are working on the cadmium tolerated solar cell with First Solar company, the First Solar company is giving they have a buyback policy. Like they will buy all the module after 25 years, or if they go bad, you have not to throw into the environment, because people have raised the concern of cadmium, because cadmium very toxic or carcinogenic. So if you throw into this earth, so very harmful. So they have the buyback policy. Like if you are purchasing from them, after 25 years, they will buy back. They have the recycling process also.
Okay. Thank you, sir. Sir, you have discussed applications of CIGS based cell. One question is, what are the parameters which we have to keep in mind before using CIGS based solar cell?
Initially, I told you is the major impact is the band gap. Where you can absorb most of the solar spectrum. So you can have a band gap, like silicon has only 1.1 electron volt. So you cannot absorb all the solar spectrum. In this CIGS, you can vary the band gap from 1.1 to 1.7. So best efficiency is actually around 1.2. So now the people are looking for the tandem solar cell. Like they have the silicon. On top of that, they have tried to CIGS. Even in theoretical study, they have multi-layer. So that if you vary the band gap from, let's say, you go from 1.1 bottom to, let's say, 2 electron volt to the top. So we'll absorb most of the spectrum. 1.1 will absorb certain spectrum, certain bandwidth of spectrum. But if you vary the band gap, tandem solar cell, you are trying to absorb most of the solar spectrum. But only problem is that, like manufacturing process, tandem is slightly difficult.
Okay, thank you, sir. Sir, one last question is there. How much time involves in the fabrication of one complete solar cell?
Because time-wise, generally, when you are in a production, okay, so it's a batch process. So generally, what you can say, like within this month, we can produce this much module. Lab scale, if you are trying to have into lab scale, it will take time because first you have to make a back contact because even in the research lab, you have limited facility or something. So what people are trying to do, first they will try to make a back contact, try to create certain substrate. Then in a batch, they will try to deposit certain absorber layer, and after that, cadmium sulfide. So it may take certain time. You cannot have a fixed time. But in the production, they say it is a batch process. So when you start, this production will go on continuously.
Okay,
So I don't have the exact data, but
okay. Thank you very much, sir. That's all from my side. Now I would like to call our FDP convener, Professor Dr. Seema Naik, for giving vote of thanks.
Thank you, Pankaj sir. Thank you, sir. Very good and informative session on the solar cell, and you explained in a very good manner, especially the CIDS solar cell, its material, efficiency, and challenges also. He is having a vast experience in the solar cell, so I requested sir to share your research experience in our online FDP program, and he immediately accepted my request. Thank you, sir. Thank you very much for spending your valuable time with us. Thank you very much.
Okay, thank you. Like if any of the faculty is interested to work on this, they may contact me. There's no problem. We have a lot of facility in our university also. If somebody is interested, so they can work.
Yes, sir. Yes, sir. I will share your email ID with all the participants if they want to do the research in this area.
Yeah, sure. Thank you. Thank you very much.
Okay. Thank you, sir. Thank you very much.
Thank you, sir.